In this lecture, we're going to look at section 2.3 out of the book, Characterizations of Invertible Matrices. Now, this is a fairly short section. It's not going to take too long to go through it, but it is a very important section. What this is going to do is pull together some of the concepts that we've seen and show how they form a cohesive theory and are actually the kind of the same thing when you start talking about matrices. So in this course, one of the main things to realize is that when you're looking at matrices, looking at simultaneous equations, solutions to simultaneous equations, looking at linear algebra, that the ideas that we see are all part of one cohesive theory. So we're going to be taking some of the ideas we've seen and showing how they really are the same thing, just in a slightly different form. This idea of pulling together all of the concepts we've seen so far is summarized in Theorem 8. This is a very important theorem to understand and to understand the ideas behind it. So Theorem 8 is called the invertible matrix theorem, and it says that if you start with a square n by n matrix, we have 11 things here. We've seen all of these ideas, but it says that all of these ideas are actually interchangeable. They all mean the same thing. So it's called the invertible matrix theorem. So the first thing says that our matrix is invertible. So what it means is that if we have an invertible matrix, automatically the 10 other things in this list are true as well. And the same for any item on this list. If you can show that any item on this list holds, all of the items on this list hold. So go through them. First one, that the matrix is invertible. This is the same thing as saying the matrix is row equivalent to IN. And we saw that, I think, in the last chapter, or last section, that if you have an invertible matrix, it means you can row reduce it to IN. Also the other way around. If you have a matrix that you can row reduce to IN, it means that it's invertible. So those two ideas are the exact same thing, and that's part of this theorem. Next one, there are n pivot positions in A. Remember, A is an n by n matrix, so it means that there's a pivot position in every row and every column. That's the same as it being invertible, same as it saying that you can row reduce it to IN. Next one, the equations have only the trivial solution, the equation AX equals 0. And remember, the trivial solution means that all of the variables are equal to 0, and that is the only solution. So that's the same thing as being invertible. These are all the same ideas. Fifth one, the columns of A are linearly independent. We spent a bit of time on linear independence, kind of saw what that means, how it works, but this theorem is saying that if the columns are linearly independent, it's the same as these other ideas. Point F, the linear transformation x to ax is 1 to 1. Again, we saw the idea of 1 to 1, and we saw the idea of the linear transformation, but if this linear transformation is 1 to 1, where you take a vector and it turns into A times that vector, if that's 1 to 1, and remember 1 to 1 means that if you start with two different vectors, you end with two different vectors. If that's true, then all the other conditions hold. G, the equation AX equals B has at least one solution for every B in Rn, meaning that for B, you can take any vector you want, make up any vector you want. AX equals B will always have a solution. Next one, the columns of A span Rn. Well, you can kind of see how that's kind of the same as point G. Columns of A span Rn means that you can do a linear combination of the columns to get whatever you want. Well, that's the same as G. Point I, the linear transformation x to ax, again the same one we used in point F, that linear transformation maps Rn onto Rn. Now this language is a little bit different than what we've used so far, but if you think of what it says that it maps Rn onto Rn. Onto means that no matter what you have in that codomain, you can get to it. Well, that's pretty much the same as the last couple of points we saw. It says that if you take any vector in Rn, then you can start with something else in Rn multiplied by A and you're going to get it. Same thing. Point J, there's an n by n matrix C such that AC equals CA equals IN. Think about what that matrix C is. That's the inverse matrix. So invertible means you have an inverse matrix, but it also means all of these other points. And finally, we've seen the transpose, but if a square matrix is invertible, it means its transpose is invertible as well. This is the invertible matrix theorem. All of these points are the same thing, and the connections between them, understanding the connections between them, is really the first key core concept of this course. So it's really worth taking the time to understand why all of these things are the same, give the same result, and why they are all equivalent. Okay, so now let's quickly revisit a linear transformation. So remember what a linear transformation was. A linear transformation was when you take a vector and you change it into another vector, and it only has a couple of properties. It says that whenever you do the transformation, that it preserves addition and it preserves scalar multiplication, and it takes 0 to 0. But that was a linear transformation. Okay, so the idea was that you're taking x, and the linear transformation t is you're turning it into t of x. You're transforming it, and the transformation has those properties. But remember, we also said that one of the key results was that if you have a linear transformation, really this is just the equivalent of multiplying your original vector by some matrix A. So you get that t of x is just equal to A times x. That was one of the important results we saw earlier, and where we saw that a transformation is just the same thing as multiplying by a matrix. And there were ways to find that matrix. But now what about the inverse? We also talked about an inverse transformation where you can go from your t of x back to x, and if that's linear, and if for any point in your domain it works, that there is a linear transformation that works, and it is linear, that you have this idea of an inverse transformation. So you can go from t of x back to x by using the linear transformation t inverse. Well, not surprisingly, if t is the same as multiplying by a, your inverse transformation is the same as multiplying by a inverse. So we saw this really close connection between transformations and matrices. That connection follows through to inverses. If you have T inverse, it's the same as the transformation defined by A inverse. So this brings us to Theorem 9. So Theorem 9, it really puts down the connection between linear transformations and matrices. Now this is talking about when you have a transformation from Rn to Rn. Okay, so it's a transformation from one space to the same space. You aren't going to different size spaces. But when you have that, and you have the standard matrix for T for your transformation, then saying that that transformation is invertible is the same as saying the matrix is invertible. If your matrix A is not invertible, then you don't have that reverse transformation, that inverse transformation. And moreover, this theorem says that, well, if we have that inverse transformation, we'll give it a name, we'll call it S, being the reverse transformation. That transformation is the same as multiplying by the invert matrix. And the last 2 points here kind of summarize it. That S, applying T of x, T to a vector, then applying S brings you back to the original vector. And you can do the other way around too. Applying S first and then applying T to a vector brings you back to that vector. This only works, according to this theorem, it only works if your matrix, your associated matrix to that transformation is invertible. That's the only time you can do this for all x's in your Rn. So again, Theorem 8 brought together a whole lot of concepts and showed they were the same thing. Theorem 9 shows that your linear transformations, the invertibility of linear transformations, and the invertibility of matrices are also the same concept. You're just expressing them in slightly different ways. And that's one of the things we try to do a lot in math. We try to show that even when you come at something from two different directions, sometimes you get these equivalencies that show, yeah, really you're dealing with the same thing. And these are always important results in mathematics. So that's it for section 2.3. Now this was a short section, but it really is a very important section. So it's worth going to the book to do out some problems, to work through some of the exercises that are given for this section. This pulls together all of the concepts that we've seen up to this point and shows how they are all related to each other. This is a very important concept for moving forward in this course.